Okay, we're going to talk about differentiability and when is a function differentiable and what does this mean? So, we know that the derivative gives us the slope of the tangent line at any point. So when it's a line, the derivative is just that line. I can't draw this straight. But we can see this point here where the derivative coming in from the right side is not equal to the derivative coming in from the left side. And so the derivative does not exist because remember when we did limits, limit as h approaches 0, well, I can put a one side on this of f of x plus h minus f of x. I can do this as a one-sided limit. So if the one-sided limits don't agree, the limit does not exist, meaning the derivative does not exist. Um, we have what's called a corner or a sharp corner, a cusp, which is kind of similar, but it's curving in on both of them. So those are two examples of points where the derivative does not exist. There is a vertical asymptote. The derivative does not exist on a vertical asymptote because vertical lines have an undefined slope. So that one is just getting steeper, steeper, steeper until it's going the other way. That's known as a vertical asymptote. The last one is just simply a discontinuity. A derivative never exists at a discontinuity. Yes, the asymptote, or vertical tangent, sorry, not a vertical asymptote, vertical tangent. The tangent touches it only at that one point, and it does cross. That's kind of a weird thing. But yes, that is a vertical tangent. The tangent, again, can cross the graph. It just usually touches at that one point and bounces off. This time it touches at that one point and goes through. Um, the next thing we're going to look at is tangent lines implying local linearity. Or if you look at them closely enough, they're linear. So here we have the function f of x equals it's x cosine 3x. And we see three different zooms of the graph. So this is, kind of a relatively standard zoom, goes from -4 to 4 on the x-axis and -3 to 3 on the y. This one zooms in and only goes from 1.7 to 2.3 on the x-axis and 1.7 to 2.1. Well, if I zoom in far enough, every point on this graph is going to look roughly like this diagram, which looks approximately like a line. If you zoom in far enough, all points look like a line, and that's what essentially the tangent line is giving you. The line, that little line, and then extending it out. Okay? That was all of 3.2. Should have been not a very big step. Now we're going to move on to 3.7, what's called implicit differentiation. Okay? And I'm going to change what my sharing is here. I'm going to share a whiteboard because this will be just a little easier to work with. And everything we've done so far with derivatives we've had in y equals form. Well, now they're not necessarily going to be in y equals form. For this one, for instance, we have y squared equals x. We happen to know that that's a sideways parabola. And when I took the derivative of y, I got dy dx, meaning derivative of y with respect to x. Well, now I have something that its derivative wouldn't be just 1. Derivative here would be 2y, and then I need to multiply by the dy dx. The other side is going to have a derivative, x of 1, and I wouldn't normally write this, but that would be dx dx, which, nice and handy, cancels into just a 1. So now, if I want the derivative, I need to solve it for dy dx. So I'll divide both sides by 2y. And get dy dx equals 1 over 2y. So we are asked to find the slope next of the circle x squared plus y squared. That wasn't very neat. Equals 25. That's a circle of radius 5. We want the slope as it goes to the point 3, -4. So this is going to be the slope of the tangent to that circle. Make that a little neater. So I just go about doing the derivative like normal. 2x, I don't need to write times dx dx. 2y, but anytime I take a derivative of y, I must write times dy dx. And then I must solve for dy dx. So I'll subtract 2x from each side, giving me 2y dy dx equals -2x plus 25. I will divide by 2y and get, oh, I forgot something ever so important. The derivative of 25 should be 0. That's 0. So here I get dy dx equals -x over y. So when I plug in my point, I get -3 over -4 equals 3/4 is my slope. Okay, that's my first two examples. And do this one next. Okay, so I start with 2y. The derivative of 2y is 2 dy dx equals 2x plus derivative of sine is cosine y, but then as the chain rule says, I need the inside. Derivative of inside is times dy dx. So in order to solve this, I must gather the dy dx's on the same side. So I'm going to subtract it from both sides, dy dx. And I don't feel like writing it on the second one. So I've got 2 dy dx minus cosine y dy dx equals 2x. I now can factor out a dy dx, giving me 2 minus cosine y equals 2x. And then finally, I will divide by my 2 minus cosine y. giving me a final answer of dy dx equals 2x over 2 minus cosine y. I cannot cancel those 2's because there's the minus cosine y still attached. For our next one, we are going to do a ellipse. It's kind of a funky ellipse. You can look at the drawing. So we're doing 3.7 now. This is example 4 if you want to look in the book and see the drawing. It's kind of a tilted ellipse. And we're trying to find the slope of, or the equation for the tangent and the normal at -1, 2. So I start by taking the derivative, 2x minus. I have to use the product rule on x times y. So I do the first part. X, derivative of x, derivative of the first times the second is minus y. Derivative, then I have minus x times derivative of y, which is dy dx. So that was all. Taking this as a product rule helps me generate that. My first part was negative x, my second was y. Plus 2y dy dx equals 0. I sometimes struggle to remember to take the derivative of the constants in these when they're by themselves, but they do equal 0. So now I'm going to move things to the other side and factor out the dy dx. So everything that doesn't have a dy dx is going to be over here. And yes, I'm subtracting. I just don't feel like writing. Dy dx equals negative x plus 2y. And then I'll divide by my parentheses, giving me dy dx equals negative 2x plus y over negative x plus 2y. Okay, so I found my derivative. And I can plug in my point. So negative 1 becomes 2 plus 2 over negative x is 1 plus 4, 1 plus 4. So this is 4/5. My equation for my tangent line. I'm going to write it in point slope. Y minus 2 equals 4/5 x plus 1. Equation for my normal line is going to be perpendicular to that. So I've got to use the opposite reciprocal on the slope. Otherwise, it is exactly the same as the tangent line. Oops, I forgot to close my parentheses on that one. Okay, that was example 4. Last thing we are doing is example 5, which we're going to do a second derivative of this. This is going to take a little bit longer. So we are given this equation. Oh, that's a 3. That needs to be a 3. I'm going to make this neater. This does 2x cubed minus 3y squared equals 8. So first thing I'm going to do is find my first derivative. 6x squared minus 6y dy dx equals 0. And when I solve this, I subtract the 6x squared, divide by the 6y, I end up with dy dx equals negative 6x squared over negative 6y. And I want to simplify this as much as I can because I'm going to take the derivative again. So x squared over y. Now I'm going to take the derivative again. And when I take the derivative of dy dx, I get d squared y dx squared. And for this other side, I need to use a quotient rule, which is derivative of, or bottom times derivative of top, which is, oops, let's make that neater, 2x minus top times derivative of bottom, all over bottom squared. So I'm not done though. I know what dy dx is. So I'll simplify a little bit as I go through. Minus x squared, dy dx is x squared over y squared. So I should probably simplify this a little bit. Couple options here. I like to find the common denominator on top. I'm multiplying this by y over y. These are multiplied, so that's over 1. That already multiplies out. So this gives me 2xy squared minus x to the 4th over y, all over y squared over 1, which complex fractions, remember, are multiplying by the reciprocal of the denominator. Giving me this. Or alternatively, they split up the fraction like this in the book, which cancels. You can then cancel the y squared over y cubed to 2x over y. 2xy squared over y cubed could become 2x over y. Okay, and that is the shortened version of today's lesson. Hope that helps. Feel free to ask around because there are several people in this class that know how to do this if you are struggling with what some of that mean.